Hello everyone, I'm Xiangyu Guo. This is my joint work with Guy Corsars, bounded rectangular Shili, Daniel Watts, and Jiayi Xian. The title of this talk is on approximating degree-bounded network design problems. We studied network design problems where the typical input is a graph G with edge cost C, and the desired output is a minimum cost subgraph S of G satisfying certain requirements. One example of requirement is the connectivity requirement. So for example, if we require every pair of vertices are connected, then this is the minimum spanning tree problem. If we require some subset of vertices are connected, then this is the minimum standard tree problem. And similarly, if we require there are k edge disjoint passes between every pair of vertices, then this is the minimum k edge connected subgraph problem. Another type of requirement we will study in this talk is the degree bound, where we have a bound D on the degree for each vertex, and we require the subgraph S be simple enough such that each vertex has degree bounded by D. In this talk, we will focus on the degree bounded directed standard tree problem. And we will also briefly talk about a result on another closely related problem called degree bounded group standard tree on trees problem. Let's first give the formal definitions of the two problems. The degree bounded DST problem is defined as follows. Given a directed graph G as input with edge cost C and degree bound D. And in addition, we are given a special vertex R as the root and a subset of K vertices, which we call terminals. The goal is to find the minimum cost tree T that connects R with every terminal, and T respect the degree bound. So in this example, the highlighted edges represents a feasible solution. There are a lot of related works for degree-bounded network design in undirected graphs. The most famous one might be the result for degree-bounded minimum spanning tree problem, and the result is by Singer and Rao in 2007. They gave a bicriterial approximation using iterative rounding. Here, the first number in the tuple is the approximation ratio on the cost. And the second number in this tuple is the degree violation. So it means you here the dv plus 1 means you might violate the degree bound by an additive one. For degree bounded standard tree problems, there are also some results by Rao and Zhou and also by Lewis and Vishnoi. And they also use iterative rounding. These results are almost optimal in both factors. So we can see that the undirected case is well studied. However, in directed graph, the problem is significantly harder. Even without the degree bound, the directed standard tree problem doesn't admit constant approximation. And it's known that one cannot approximate it within order log square minus epsilon k, assuming p does not equal np. And the current best approximation ratio by polynomial time algorithms is k to the epsilon, where the running time is related to epsilon. This is a very old result by Zelikovsky in 1997. Usually we can think k is of the same order as n, so this is essentially a poly n factor approximation. If we allow quasi-polynomial running time, then there is an almost tight approximation algorithm by Grandoni that calculate and Lee, and also independently by Guggen and Lagrange. And the two authors are also authors for the current paper. Our main result for this problem is a randomized approximation algorithm with quasi-polynomial running time. This is the first non-trivial approximation algorithm for this problem. And we achieve our approximation ratio is not too far away from the optimal. So we have order log n log k approximation ratio on cost, but we violate the degree bound by order log square n factor. And there is a omega log n lower bound on the degree violation, and this is by a simple reduction from set cover. Our algorithm is based on rounding a novel LP formulation, and our algorithm can be generalized to handle constraints other than the degree bound. Our second result is on degree bounded group standard tree on trees. Now the input graph is itself a tree and is undirected. And we have edge cost and degree bound as before, but now the terminals are partitioned into k groups. And the desired output is a minimum cost tree such that it connects the root R with every terminal group. So you only need to connect one terminal from each group. And also we need to respect the degree bound. So this is this highlighted edges are example of a feasible solution. You can see that each group is only one vertex from each group is connected by this tree. So why do we study this GST-on-trees problem? First, the hard instance for the omega log square n lower bound of directed standard tree is essentially a GST-on-trees instance. And our algorithm for the degree bounded DST problem can be viewed as converting the input to a GST-on-trees instance. So our algorithm for this problem is a polynomial time approximation algorithm, and it achieves almost a tight approximation ratio on both the cost ratio and degree violation. And this results improves the previous results by Cosas and Newdorf, and we shove a log n factor in the degree violation. The rest of the talk will be focusing on algorithms for the degree bounded DST problem. We will first show how to convert a DST to another object called state tree. And this can be viewed as an encoding of the DST. Then our algorithm will try to find the state tree that encodes the optimal DST using linear programming. In the first part, we can forget about the degree bound and only think of how to find the DST. We then show how to incorporate the degree bound into our algorithm, and finally, how to run the LP solution. First, let's do some pre-processing. We can assume that every terminal of the input graph is a leaf. So otherwise, we can add a vertex to make the terminal a leaf. Also, we can assume every vertex has outer degree 2. And if not, we can replace it with a gadget. And this gadget is just a 4 binary tree. So this can make every vertex have outer degree at most 2. But this pre-processing can change the degrees of vertices. So we need to remember the original degree of each vertex. but this is not difficult. Although I'm not going to talk about how we will do it, you can just trust me that the degree is not a problem. We first define a concept called decomposition tree. Roughly speaking, it encodes a specific way to partition a binary tree. So suppose we have the input graph G and root R, and say the tree T is the optimal DST in this graph. And it's well known that one can break a binary tree into two subtrees that are of roughly the same size, and the two subtrees are connected by one vertex. This is given by the so-called balanced partition theorem. And in this example, we break T into T1 and T2, and they intersect only on this vertex R prime. We can recursively apply the balanced partition theorem until every subtree is small enough. So let's look at this example again. First, each node in the decomposition tree will remember all the vertices in the current subtree. So initially, we have the whole tree T. So the node contains all the vertices of the tree T. Then apply the partition theorem. We get two subtrees, and we create two nodes with corresponding vertices. And we continue this process to break the tree into pieces until it cannot be partitioned anymore. And it's easy to see that this decomposition tree is of size order log n, since if you assume the original graph is of size n, or has n vertices, then the depth of the decomposition tree is clearly order log n. And we can, given the decomposition tree of T, we can recover T by union all the leaves of the decomposition tree. This decomposition tree is a simple way of encoding a tree in the original graph. It has some nice property. Specifically, it's a full binary tree of order log n depths. So it's well structured, and our goal now is to find the decomposition tree corresponding to the optimal DST. To be precise, we will define a more succinct version of decomposition tree, which we call a state tree. This is because each node of the decomposition tree contains too much information, and it will be difficult to search for a decomposition tree. Like the decomposition tree, each node of the state tree corresponds to a subtree in the original graph. But instead of remembering all the vertices in the subtree, we will only remember the root of the subtree and the portals we use to glue different subtrees. In this example, we look at this node in the decomposition tree, which corresponds to these 5 vertices subtree E, F, G, H, I. And we break it into 2. But in the state tree, we only remember the root of the subtree and the portals. Here, the portals are vertices we choose to break the subtrees, or you can think of it as vertices we use to glue subtrees together. So initially, in this subtree, we only have one portal E, because this is the only vertex we use to glue this subtree with the subtree above it. After we partition it into 2, we have one more portal F, and this portal F is also the root of the one of the subtree. A crucial, let's first see a more complete example. The one on the left is a decomposition tree we obtained previously, and we show the corresponding state tree. So initially, the subtree is the whole tree. So the root is R, and we only have one portal, which is R itself. Then we break it into two, and if you remember, we break this subtree at vertex E. So we create a new portal, and this subtree inherits the portal R and also the new portal E. And the new portal E is the root of this subtree. And we continue this process to get a subtree of to get a tree of the same depth as the decomposition tree. And this is what we call a state tree of T. A crucial observation on the state node is the largest portal set in the optimal state tree is of size order log n. To see this, consider partition a subtree with state R prime S, which just corresponds to a subtree rooted at R prime with portal set S. And suppose we break it at vertex R double prime, which means we will introduce one new portal. And we divide the original portal set into S1 and S2 and assign them to the two subtrees. And this process will introduce one new portal in each partition. Recall that the root state is R with a single portal R. And the tree is of depth order log n. So it's easy to see that the portal set can only grow to size equal to the depth of the tree, which is order log n. To summarize, we know the optimal state tree has the following properties. First, it's rooted at a state with root R and a single portal R. And the optimal state tree has depth order log n. And each internal state in the optimal state tree has a portal set of size order log n. The key idea of our algorithm is that we can somehow enumerate such state trees in quasi-polynomial time. So by such state tree, I mean state trees satisfy these three properties. To enumerate those subtrees, state trees, is essentially asking how many such state trees are there. To count this number, we consider the number of possible ways to partition a state PS. Remember, this state represents some subtree rooted at P with portals S. And to partition it, we will choose a new portal P prime. And we divide the original portal set S into S1 and S2. So the number of possible ways is at most the number of choices of P prime times the number of choices for this partition. And this is at most the number of vertices times 2 to the size of S, which is polynomial in N. And here we use the property that S is of size order log N. So if we let T circle be the union of all possible state trees rooted at this root state R, and with depth order log N, and satisfy the property that every state has portal size at most order log N, then it's easy to see the size of this tree is quasi-polynomial in N. This is because each level, the number of nodes grows by a poly N factor. So here, to make the drawing cleaner, I defined a new type of nodes called virtual node. It's this triangle node. It just represents one way to partition a state. So each possible way for partition a state will correspond to a virtual node. So by definition of T circle, it must contain the optimal state tree as a subtree. And if we let xv to be the indicator variable of whether the node v is in the optimal state tree, then we can convert the linear programming relaxation for DST to an LP on the variable in variables x. This is a very rough sketch of the LP formulation, and I'm not going to explain what each constraint means. You can trust me, it's quite straightforward to write down once you have the tree T circle. And this LP is of size polynomial in the size of T circle, which is also quasi-polynomial in N. Now we return to the problem that's ignored previously, the degree bound. It turns out we can simply incorporate it into each state node. So now each state node contains 3 pieces of information: the root of the subtree and the set of portals. These two are as before, and we also include the outer degree of each portal. And when we partition a state node, which means we create a virtual node, we need to specify the new portal and the portal set partition. These two are as before. And we also need to specify the outer degree of the new portal. With this modified definition, we count the size of the tree T circle as before. So we ask the same question: what's the number of possible ways to partition a state? And it's easy to see that the answer is still polynomial in N, since we will just times additional dp factor, and this is at most N. Here, remember, recall dp prime is just the degree bound, and this number is still polynomial in N. So the size of the tree T circle is still quasi-polynomial in N. Now suppose we have got the LP solution. We use this simple recursive rounding algorithm to round it. So given a state node P, we choose a virtual node Q with probability XQ over XP. This just means we randomly choose a partition of the state. And then we recurse into the resulted 2 substates. After that, we continue the process. This algorithm is proposed by Gag et al. At 2000. And they show the resulted tree has some good properties. So formally, let tau be the state tree returned by rounding. And let T0 be the tree encoded by tau, by the state tree tau. So now T0 is the tree in the original graph. And we can show that the expected cost of T0 is at most the LP cost. And T0 respects the degree bound. But T0 may not connect every terminal. However, it connects each terminal with not too small probability, say omega 1 over log n. Now the main algorithm is easy to see. You just simply run the round procedure multiple times independently. So we run it for Q times, where capital Q times, where capital Q is of order log n times log k. Then we take the union of all the outputs. We can show that with probability at least 0.9, the output connects all terminals. And furthermore, each vertex appears in the output for at most order log square n times. Now combine theorem 1 and theorem 2, we obtain the claimed approximation ratio for both the cost and the degree violation. So in summary, we give a quasi-polynomial time algorithm with all the log and log k approximation ratio in cost and log square and degree violation. And we want to emphasize that the degree bound is handled by simple enumeration. We don't use any special structure of this constraint. That means our algorithm can be easily generalized to handle other constraints, as long as it can be enumerated in poly n time. So we will still get a quasi-polynomial n size tree, the T circle. And in particular, our algorithm can reproduce many results of Cook and Lagrange 2020. So that's all. Thank you.